In activity 4 of our binary counters tutorial, we're going to be looking now at a different counter which is known as a 4029, which is an up-down, divide by 10 or divide by 16 counter. It's also synchronous. We won't be too interested in what that means right at the moment. Now you can see that there are lots of pins here, and perhaps it's obvious which ones we might be using. For example, the outputs would be A, B, C and D in the normal way that we have a 4-bit output. Our clock is pin 15. Our power pins are pins 8 and 16. But then there are lots of other pins there as well. So once again we need to look at our data sheet to make sure we understand what they all do and which ones we need to connect to make this circuit work. So it tells us straight away it's a programmable counter. In other words, we can have two different types of output. One is a decade divide by 10, or one is a hexadecimal divide by 16. And it is an up-down counter. In normal operation, load and enable are held low. So let's write those down. First of all, load, which we can see is pin 1, is meant to be low. And enable, which is our pin 5, is also meant to be low. If pin 9 is positive, and pin 9 is our bin BCD pin, which is binary or binary coded decimal, if pin 9 is positive, the package counts by 16s. If pin 10 is positive, if pin 9 is positive, the package counts by 16s. But if pin 9 is grounded, the package counts by 10s. We're going to count by 10 first of all, so we will put pin 9 low. So this bin BCD pin, which is pin 9, we are going to put low, which means that we are going to count in BCD mode, i.e. base 10. Next, if pin 10 is positive, the package counts frontwards or up counts. That's definitely what we want to do at the moment. So we're going to put pin 10 positive. So our up, down pin, which is pin 10, we are going to put high. So it counts upwards. Now we know that our outputs are A, B, C and D. And you'll also notice here that there is no reset pin. And there is a very good reason for that, which we'll look at. So, the last pin is pin 15, which is our clock. And that, of course, we're going to feed from our function generator. So let's have a look and look at it count. With all those connections made, we can see that this counts from 0 to 9 and resets. And that is without the use of a reset pin. That's because we have set pin 9 in BCD mode. In other words, binary coded decimal, where it counts from 0 to 9 and automatically resets itself back to 0. If we were to put pin 9 high, let's see what happens. There it's gone blank. So what is happening is it is counting 0 to 9, then of course our 10, 11, 12, 13, 14, 15, 0. In other words, it's gone back to that 4-bit counter without any reset on it. I'm going to put that pin back low again so that it counts normally. Now another interesting pin on this one is pin 10. This is our up-down pin. I'm going to connect pin 10 low. In other words, I'm going to take out the pin that's already there and connect that directly to ground. And there we go. You can see that now, instead of being in the up count mode, it is now in the down count mode, and it counts from 9 to 0 and then resets, if you like, back to 9 again. Let me put that back high again, and it immediately starts counting up again. Just by way of explanation here, we also have what are known as parallel loading pins, which are our PA, PB, PC, PD. And that means that you can start the count at whatever number you want it to. So if we loaded 0001 into it, so that is A is 1, which is a 1, it would start counting not at 0 but at 1. And finally, with these circuits, we can join them up to second circuits so that we can count to 99 like we did in our previous activity by using the out pin. If we look at that out pin, currently it's high. Watch what happens when it gets to 9. It goes low. So we can feed that out pin to the enable pin of the next stage, so another 4024, to its clock pulse. And by the nature of that going low, it will provide a clock, and the next stage will then count. So in essence, if it was 0 on the next stage, it would go 1, 2, etc. This is the end of activity 4. In our final activity on binary counters, activity 5, we're going to be looking at the 4026, which is a decade divide by 10 counter with 7 segment decoded outputs. Now this is a really useful IC if you want to count to 9, then go back to 0 and drive a 7 segment display without the need for all the wiring and the decoding going on that the 4511 uses, and of course building all your D-type flip-flops. In other words, this chip pretty much does it all. So once again, let's look at all these pins. We know therefore that A, B, C, D, E, F and G are our outputs, and they are going to go to the 7 segment display. We have a clock coming in, which is pin 1, and then we've got these unusually named pins here. So let's have a look at what we need to do with those. In normal operation, reset and clock enable are held at ground. And I think we'll pretty much be using normal operation. So reset, which is pin 15, that's going to go to ground, so that's going to be a low. Our clock enable, which is pin 2, is also going to go to ground. It then goes on to say the display enable is held positive. So our display enable, which is pin 3, goes high. That needs to be positive. That's enabling the display to output. So we've got our clock, which is pin 1. So let's look at the circuit. It's built as we've wired up the pins, and we can see it counting. So it's counting 0 to 9. I'm just going to crank up the frequency just a little bit. Counts 0 to 9 and then resets. Perfect. We haven't got the 4511 doing all the decoding and therefore the driving of that, and we don't have all our D-types. All we're doing is feeding a clock in from our function generator, and away it counts. Let's just look at a couple of those extra pins. Let's look at that 2 out, which is pin 14 first of all. And there, perhaps unusually, you notice that as it reaches the count of 2, it goes low. That's a slightly unusual output, and you may find a use for it in the future. Let's look at pin 5. So pin 5, watch, there we go. And what this is doing, it says it's a divide by 10 out, but in fact what it's doing, it's dividing the clock pulses up into 2, if you like. So on counts 0 to 4, the output was high, and on count 5 to 9 the output is low. Let's look at one more feature of this chip, and that is the reset pin, which is pin 15. Currently it is low, as it said in the data sheet. I'm going to remove that reset pin, and immediately the counter has stopped. Press it, and now I'm going to put that low again, so it starts counting. And the second I remove it, it resets itself. Now it says that you should really put that high, but it's recognizing a high as soon as I remove it from the low. This is the end of our binary counters tutorial.